Welcome to EDU World Space.
So this problem describes the following situation where we have one mass at the origin m1, another mass m2 3 meters higher up, and then mass m3 4 meters along the x-axis away. And we want to find what the gravitational force on m3 is from these other masses, and we're given values for these. So to start, I'll fill in the rest of this as a triangle. So if one side is 3, the other side's 4, and this is a right angle, we know then that the hypotenuse is going to be 5 meters. And this angle theta right here, we could calculate as 53.1 degrees. So I just did inverse tangent of 4 over 3 to get that. So we want to find the force in M3. So we'll do this in x and y components, and then we'll combine them to get the net force, and we can also find the angle. So we'll start with the x force. So it's going to be the gravitational force times M3, and then we'll have forces from M1 and forces from M2. So for M1, that one's easy because it's right along the x-axis. So that's just going to be M1, and the distance is 4 meters, so 4 squared. And then also in that same direction, so this is pulling to the left. This one is also going to be pulling it to the left in the x direction. So then we'll have plus M2, and its distance is 5 meters, so 5 squared. But then we only want to take the x component of that. So we want to do sine of theta to get opposite this distance over hypotenuse. So then times sine of 53.1 degrees. And so we plug in m1 is 50, m2 is 80, and we should get then that this force is 1.89 times 10 to the minus 10th newtons. And that is in the negative x direction. Those are both pulling to the left. So for the y force now, we do the same thing. We have g, m3, and then mass 1 is going to have no y force since it's parallel with m3, so we only have to worry about m2. So we have m2, its total distance is 5, and then square that again. And then rather than doing sine, now we want to do cosine to get adjacent this component of the force. So then cosine of 53.1. And we should get then that is 6.41 times 10 to the minus 11th newtons. So we can draw our forces out here now. So we have this y component, and we have this x component. And we want to find the net result of these two. So F net. And so we can just do that with the Pythagorean theorem. So we'll say F net is the square root of fx squared plus fy squared. And so when we evaluate that, we should get 2.00 times 10 to the minus 10th newtons. So that's the magnitude of the force. We also want to give the direction. So we could find this angle here on the force. And that would just be inverse tangent of Fy over Fx. And when we do that, we should get 18.73 degrees. But to give kind of the more standard answer, usually we want to give the angle above the x-axis. So this is kind of pointing like this. And instead, we want to give this angle here. So that'll just be 180 minus the angle we found. So 180 minus 18.73 tells us that this is about 161 degrees above the x-axis. So this was part A. Part B now asks us where other than infinity could we put this third mass so that the net force on it is 0. So thinking about the x forces first, it's clear we have to put it like in line with these two masses. So anywhere else we put it, there's going to be a net X force on it. So it has to be somewhere along this line here. And then similarly, we can say it has to be between these two masses. So if it was below, it's going to be pulled up. If it's above, it's going to be pulled down. So there's some spot in the middle where M2 pulls up, M1 pulls down. They balance each other out. So it's got to go somewhere around here. And I'll call this distance from the origin x. So that will be the distance from M1. And that would mean then that for M2, its distance would be 3 minus x. So we'll do this on a new page now. So part B, so we've already determined that the x position has to be 0 for there to be a net force. And so for the y position, now we want to say that we want our net y force to be 0. And that force on it should just be G M3. And then we have the force from mass 1. So that's going to be pulling downwards on it. So I'll say that's a negative force, and it's a distance x away. So we have M1, and then we have that over x squared. And so that's in the negative direction. And then for our other force for M2, that will be in the positive direction. That's a distance 3 minus x away. So then we have plus M2 over 3 minus x squared. And so we want this whole thing to equal 0. So that means that this product here has to equal 0. So that tells us that this term has to equal this term. So, or rather, have to equal the negative of each other. So m1 over x squared negative has to equal negative m2 over 3 minus x squared. And so that'll mean that this whole inner term is 0. So can get rid of those negatives, and I'll save you the algebra on this, but you'd kind of multiply these on both sides, do a little bit more algebra, solve for x, and we should find that x is 1.32 meters. We can check and just make sure that seems reasonable. So mass 1 is lighter than mass 2, so at x being 1.32 meters, that means this mass is more like right here. So it's closer to M2, which kind of helps compensate for the fact, or sorry, it's closer to M1, which helps compensate the fact that M1's a little bit lighter, then it's farther from M2, but it's heavier. So it seems reasonable they're able to be in equilibrium here.